So smart energy. So let's change gear. I hope that through this presentation I will make you a little bit of a power systems engineers as well. So let me give a little premise first. Oh, I need this. A little premise which sort of is repeating some of the concepts. What we want to communicate and compute really depends on the application. And what we want to communicate oftentimes is some feature or description that is useful to make a decision. In the application that we saw at lunch, we actually want to know what is the gas emission of that car at that time. And perhaps the conclusion that we want to make are policy conclusions. So you have to wonder, where and why certain real-time communications are needed, and what really do you need to send, and how much of these computations can be done locally. So if you just look at abstraction, and I intentionally didn't cover this part. In fact, there was a question that came after the morning that said, well, Professor Scaglione, have studied a theory of computation which is information theoretic. What is the rate at which I have to transmit to perform a certain computation? And I stayed away intentionally from that. I kind of switched gears and I talked to you about multi-agent communication because, again, the setups for which we can say something are somewhat artificial. They don't belong to real application. While multi-agent communications, multi-agent protocols, I've given you an example where I could use it actually for state estimation on the grid. That was the example that I made of the Gauss-Newton algorithm, right? So that could be exactly applied in that form. So I think that the problem that exists of finding general abstraction is there. Multi-agent computation is somewhat a general abstraction. Others are not. A lot of the information theoretic results for the moment are using quite artificial abstraction. So in that application that I showed you of multi-agent protocols for the power grid, I was trying to solve a nonlinear least square algorithm to get the state of the system. So imagine that you want to get a map of all the gas quality, right? Since it diffuses, it will be a smooth field, so you want to know that, right? But what I want to talk to you about is why would I need the state of the grid? Like, why is that useful? Because from the communication perspective, a power engineer can come to you and say, give me the state, I want it at this speed, et cetera, but why do they want it? So I'm trying to argue in this part of my lecture, why do you need it? And I'm trying to move you away a little bit, kind of lift a step above the IoT, right? So the infrastructure that the IoT serves. Because a lot of the discussion that is also happening in the communication community that pertains to smart energy is really quite local, is looking at a very standardized way of dealing with the power systems problem that may not be the best one. So what people are thinking about right now, prevalently in the smart energy arena, is that they will connect to a network that the utility has to put in place, right? So this figure is not particularly high resolution, and I apologize for that. But imagine this is your house. You have the dishwashers. You can delay the dishwasher. You have other devices that are connected through the network, but the home energy management system that is controlling also your water heater and whatnot, and your electric vehicle, what it's trying to do is trying to communicate to the utility network, to this magical smart meter that will go to a fabulous network that the utility has put together for you. So your problem of smart energy is very much confined to a house, or perhaps if it is more challenging, to a building, right? And if you have a multi-story building, that's not trivial, but it's still a very local problem. We're not talking about a large infrastructure. So you may argue, like, why is she talking about great distances, et cetera, et cetera? All I have to go is to the AMI, which is the wall of my house, right? And in fact, all the discussion about Zigbee smart energy, which is in the standardization of this application, is really trying to just have this very narrow view of what smart energy means. And the assumption is that what I want really is to have a library that tells me what type of applications and what type of devices I'm communicating with, right? What type of interfaces I have. So you have all of these things that are put together here. You have the ones that are relevant are the Zigbee smart energy, and I would say also the light link is control of lighting, but control of lighting can become part of the equation. And you want to consolidate this application layer. And the important thing that you want is to get to an IP network, right? And you may, in the vision that I said before, this IP network would be a network which is interfacing towards the utility, but it could also interface through another network to some service provider, maybe those that leased you the home energy management system, and they may reward you for giving them some control. And what Zigbee is really codifying in this smart energy interface is what the utilities prevalently think is going to be the great idea, the thing that is going to save the planet. Here is your AMI, right? And they are deployed right now. They are metering information. They are trying to reality check what you are consuming, but they're not really telling you to do anything. But the dream of demand response from the utility perspective is that they're going to send you a price signal. So they're going to send you a price signal which will be computed in quotes and quotes real time. The real time will depend on a bunch of consideration, not including the latency with which they can actually compute it and send it to you. And this will communicate with your home energy management system that has an interface. The human will interact with the interface, but the real-time control will be an algorithm that is incorporating the preferences of the consumer in some way and trying to get electricity on the cheap because of the price. And the way they want to see this is that essentially what this price signal is trying to do is trying to say, sell me some megawatts. What are the megawatts? They are not consuming a certain amount, right? So it makes me laugh, and I'll tell you why. So they assume that there is a baseline that you want, and that you are going to sell them your deviation from the baseline. Why? Because they want to see you as a reserve, as some kind of generator, right? So if you remove some of your consumption, it's as if you were generating what was needed for you, right? So they don't have to activate a natural generator to produce this energy. They can do without, okay? So this is, from a communication point of view, is actually not that great. Why? Because it's like in the gas pollution case where you have to monitor constantly, right? Why? You have to measure constantly what this person is doing, because the price you're going to offer will be a function of what this person is doing. So you are kind of continuously monitoring the activities, so you have a constant bit rate source, which is sending you samples of this consumption signal, and then you have to broadcast the price. That's not too complicated. You can do it in various ways. But it's the uplink which is a little bit problematic, because even though this is a fairly smooth signal, so to speak, I mean, you could send an average and get a reasonable decision framework. You have to have every house send this constantly, right? So the question is like, do you really need that? The other point is that, knowing how much time my son or my daughter, I don't have a son or a daughter, takes to shower, I mean, maybe for me it's interesting, but why should the public utility know that, right? So it's a very intrusive system. And even if I don't mind that they know how long it takes for the shower, privacy comes at the loss, because a utility, the retail market of electricity, is, at least in the United States, a monopoly. So I don't have an alternative that I can go to another wire. So if this entity knows exactly when I want to consume, what prevents this entity to jacking up the price just because I want that good at that time, right? If they can send a price signal which is designed for me and there is no competition, there is no particular reason why they should be, unless you regulate them, and even if you regulate them, it will be really hard to check. There is no particular reason why they couldn't use it to price you differently because you really want to consume power. You really want to take a shower at that time, right? You don't want to take it at another time. So they're going to make you pay a lot when you want to take a shower, okay? So privacy in this sense, in a monopolistic environment, is actually important economically for the consumer, okay? I already said it's inefficient and slow. And as a matter of fact, this is another feedback control loop. So if you don't know how this guy is responding to this signal, you introduce more uncertainty in the system. And as you will see, uncertainty is what primarily raises cost in the grid. Okay? So I don't like it. I don't blame the Zigbee folks for doing this because all the utilities are saying that that's the way you have to do it, right? But I want you to understand this problem, and maybe I'm wrong, and I would be really glad if anybody eventually over the years proves me wrong. But I have all these issues with this that I just read. But everybody is kind of following in this kind of bandwagon, and then other people are getting these smart energy devices certified because AMI have been deployed and they want to sell tablets and other things to do home energy management. Smart appliances is the other big thing, right? And it's all creating sort of an ecosystem of devices that can talk, they are compatible, they are on the same network. And these are the primary certifiers of these type of devices. And you know, Zigbee, home automation, like these have other applications that have nothing to do with what I said, with pricing electricity. It's just convenience, right? That you have things that you can do remotely and control remotely. So there is another part of this equation that obviously has nothing to do with the scheme that I talked about. So I think that this is a much better scheme, and I will try to explain towards the end how you reach this scheme. So instead of tracking continuously individuals, and again, remember, utilities are monopolies. You have only one wire. You don't have an option, right? You cannot get a cheaper price from another wire. What I think is that the utility should not see the individual consumption at a time. They should have a description of the devices that are online that shows what features and what kind of control they can perform. After all, these appliances, when they use electricity, they're really boring. It's very predictable what they are going to do. So why monitoring like this is a new phenomenon every time? Every time the printer turns on, it will do that wiggle. It's always the same. Okay? So those features can be abstracted away, and we can look at this aggregation as sort of an event-driven process where I know there are online these controllable devices that arrive in my system and they have a service. And so what they have to communicate is really what kind of service they want. Okay, so this is the aggregation of this information. So I now don't have a one point-to-point link from every household to this AMI network. What I really need is an aggregate description. So they have to notify me of what devices are online, but that's pretty much it. I don't have to refresh the state constantly. And again, on the other direction, I do have to broadcast. I want broadcast a price. I have to find a way of broadcasting this instruction for these different kind of devices that is fairly efficient. Okay? And this aggregation is not looking at every device as it has the same behavior. What it's trying to do is to classify the devices based on the fact that they have similar behavior. And there are just a few features that characterize them. So the charging of an EV battery is just few parameters that you have to figure out, right? If you know the brand of the car, you will know what is the rate of charge, what is the capacity of the battery. So if you can classify that, and many different vehicles may have actually the same type of rate, the same type of batteries, the same type of capacity. So in that case, they belong to a blood class, right? And all I have to know is that I have this request and what is the state of charge of this battery, really, okay? So that's the idea of conveying this information. And I don't need to know at the time in which these data arrive, really who is that possesses that particular electric vehicle or dishwasher, because if I am clever, I will know how to broadcast instructions so that they know locally whether they are they have to operate or be off at that particular time. So that's important because now I can design incentives that are equal for everybody that provides flexibility in a certain class. Okay? And the classes are also useful for me because what flexibility I get from an air conditioner is very different from the flexibility I get from an electric vehicle. So why should I reward these the same? It doesn't make sense, right? While the unique price that I get from the pricing mechanism is tied to the in the back-end to figure out how all of this stuff that you have at home will respond to make a unique price for electricity. Okay? So this is a service-oriented model. So I like this, and I will show you why I like this even more if you think about smart energy at the higher level. Like, so what, you know, the people that design the power systems infrastructure are thinking. For that, I will give you some insight on the mathematical equation that govern power delivery. I mean, all it requires is really some understanding of circuit theory, right, and transmission lines. For those of you that have studied DSL or copper wire, maybe in these ancient books that talk about telephones, right, you have actually seen these transmission line equations before, and so this is just trying to abstract, it's the same exact type of equations which are applied just a little bit differently. Okay, but first of all, I have to give you a sense of the scale. Okay, so today, most of the power that is delivered is not delivered through really tiny microgrids that serve a small community. It's just produced in bulk by large plants, okay? These are coal, nuclear, and increasing natural gas power plants, particularly in the US. So, and there is an economy of scale. It actually is better to have larger scale plants because they do pollute less. And a large power plant, just to understand the scale, is about 1 gigawatt of power, right? For small cities, a power plant can be also from 40 to 100 megawatts of power. So one home, not necessarily a very big home, is consuming between tens and thousands of kilowatts hour. So if you have a large power plant, you are serving millions of people, basically, right? So you have this one huge control knob for many uncontrolled places, users. So just to give you a sense, and I will have actually an interesting example later on that pertains exactly to California. California is 50 gigawatts of peak power consumption, which happens in the summer. California is a pretty densely populated state, so it's not unreasonable. So you can 50 large power plants will serve California, right? What is power? Remember, power is the derivative of work, right? And it comes in many forms, and so it has different. We measure it in watts when we think about electric power, but it could be measured in joules or calories, right? So these are different units that are more appropriate depending on whether you look at electric, mechanical, or chemical power. Okay, and so there are three ways we can transfer energy. One is heat, right? And how does heat propagate power? Because of essentially vibration, right? So there is mechanical work that you do if you displace mass, and electrical work is when you displace charge. And that's the best kind of work if you want to cover a big distance, because it's very fast. It's a very fast process to displace charge, much better than displacement of mass, or it has a much better ability to transfer also than heat, because heat is very slow, right? And that's why I say, when I advertise for electrical engineering, I say we are the fastest. We do computers, communications, electric power, because we are the fastest, right? We move at the speed of light. Everybody else doesn't, right? So we deal with the fastest stuff. So the voltage is, what is voltage is essentially an electrostatic potential. So you can just see like, oh, there is a high voltage. It means like you are on top of a hill and the charge wants to go towards the bottom of the hill where the voltage is lower, right? So this charge is kind of running down this slope. So is work normalized by charge, and is also the integral of the electromagnetic field over a certain path, okay? And power, being the derivative of work, can be written as the derivative of the voltage times the current divided, VQ dt, right? So, but if the voltage is constant, then you have the Q dt, which is the current, right? The current that moves per unit of time, okay? So that's why power is V times I, right? And I think everyone here in this audience remembers it, but it's kind of nice to remember this equation, because you will see that it has an effect on what I want to balance in power systems, right? Okay, so we want to deliver a certain power P, and what we are constrained with is this product. Really, right? Why is we are constrained with this product? Because the current has to flow through a medium, which will be these transmission lines, right? So they are constraints because we cannot transmit an arbitrary current through the transmission lines. They will heat up, they can melt, right? So we have limitations. And the voltage also cannot be arbitrarily large. And so that's a limitation on how much power we can transmit over the network. So that creates really the congestion. The very important part that connects us to all kinds of uses, particularly if we want to run a motor or we want to generate power through a motor, so through using, as we said, fossil fuel, are the electrodynamics law. There are two laws, Lorentz and Faraday laws. And what this does, it connects essentially this motion of charge with an actual force that you can utilize to move stuff, right? There is another important use of this, in particular Faraday law, is used in transformers, right? And they allow to go from a higher voltage level to a lower voltage level. And the reason why that's very important is because if you have higher voltage, the loss that you have with the thermal loss that you have in transporting power is actually lower. So you want to transmit power at a very far distance at very high voltages, and then you have to scale it down because otherwise people will die, right? So you don't want to have, in the proximity of a house, you don't want to be at a very high voltage. Okay, and by the way, the very fact that you use transformers which are basically made like big coils is what determines the fact that we use alternating current instead of using DC current, right? Today that wouldn't be necessary, but at the time, there was this became the prevailing argument towards producing power which had an alternating current that going up and down. Okay, so there are 4 sections on the grid. There is what is called generation, right? And this side of things is studied by electrical engineers, but also by mechanical engineers, because the production is typically through chemical processes that then are translated into electric power through turbines. Then there is the transmission section, and is medium to high voltage section. So transmission and distribution is really looking at systems that are conceptually the same, except the transmission section of the network is the one that covers the very large distances and is typically a kind of mesh network of wires, while the distribution is the set of feeders that arrives to the different homes. And so the transmission points are this big substation that then have all these feeders that branch out and go to different homes. And occasionally in the distribution network, you have a medium voltage network that has some cross wires, but oftentimes those are open. So usually the distribution feeders operate like a tree, right? That is sprinkling down the power to the different consumption points, while the transmission network is this mesh, which is kind of a pool where you try to get power from different points where the generation, the bulk generation resides. And so far, the generation typically goes from the core to the edges. The edges do not provide, you don't get power from the distribution network upward, right? Even though there is today a lot of renewable power, which is solar PV rooftop, and if that becomes excessive, you will have to ship power from one substation to another one. The consumption level is at the low voltage level, and these are the home circuits. They go from a neighborhood feeder to your home. Okay? So generation, we like not to think that, like everybody's talking about solar power, wind, we have so much of it. But in fact, almost all the electrical power today is, and wind also applies, this applies to wind as well, is produced by some kind of turbine. Most of them are steam turbine. And there are various basic design. The more widespread design is this Pelton wheel, you spray water or vapor, and you turn it around, and this creates, if you have a magnet, creates a current that will generate power. But you also have wind turbines. The principle is just that the fan is actually creating the rotation, and there is a Benz law that says that you can at most convert 60% roughly of the wind power into mechanical power of these turbines. And as I said, we produce an alternating current, and typically you produce it on different windings. The normal scheme is that you have 3 wires, and you typically send an exactly equal voltage signal to each of the 3 wires, and that's called balance. This is called the 3-phase circuit. So oftentimes when we describe power systems, we only look at 1 voltage, but in fact there are 3, and they're perfectly balanced. So from one you can reconstruct perfectly the other ones, because there are these sinusoids that go 30 degrees of phase, right? So you don't really need to describe all the relationship. There is a simplification that takes place. Okay, so the all important thing is that you have to find some means of rotating this rotor, and that's where the fossil fuel come in. You just burn stuff, produce vapor, and then you turn the turbines, right? So there are these equations that are called the swinging equations that tell you essentially what is the difference between the mechanical energy and the electrical energy. You would like to have balance, right? You would like that the mechanical energy and the electrical energy are equal, right? But here is the angular velocity of your wheel, so it's a differential equation that you have there, right? And this angle is related directly with the angle that you see, is the phase angle, the phase at which those sinusoids start, right? So the peak of that sinusoid depends on what frequency you have and what phase you have here, right? So in Europe they're 50 hertz, in the US they're 60 hertz, But basically that's a nominal frequency, because actually the frequency changes constantly with any imbalance of this. So if you draw more power and you are not producing more vapor to turn the wheel, right, there is an imbalance here, and this creates a change in the angular velocity, which creates a change in the frequency of the sinusoids. So they will slow down or go at a faster frequency depending on that. And that's really these nonlinear differential equations are what complicates this whole business, the interaction with the mechanical world. I would say there are also other nonlinear equations that we'll see are due to the balance of power, because you reason in terms of power rather than reasoning in terms of current and voltage. But all of the things that power systems engineers, the hardcore, are scared about is that you will have these gigantic turbines that swing too fast. So what they do is just essentially they take it off, right? These wheels cannot. They have a lot of inertia, but you cannot create a tremendous imbalance, because then the system could go unstable. Okay? Any question? There was a hand raise. Is it okay? All right. So basically what you can see from those equations is that if you have more electrical power requests, you're trying to draw more electrical power than the mechanical power is at that time, then the frequency will slow down, right? And instead it will rise when you are producing in excess, right? So you don't like either situation. You like to, as much as possible, to be synchronous and to be with a stable frequency, because you want all these wave of power to add nicely and constructively. And so this is a very simplified model to understand the notion of transient stability. And if you talk to a skeptical power engineer, they will think that you know nothing because you haven't studied transient stability. Right? So I warn you that this is something that is very specific. And why do power systems engineers study this in particular as opposed to control engineers? Because if you look at it as a really as a control problem, these are really difficult non-linear equations which control engineers haven't found a way to solve. In other words, they haven't found an appropriate feedback system for which they can guarantee that they will actually be able to stabilize this system. Okay, so these are complicated systems to control on the control framework. And in other words, you won't be able to determine exactly what is the local law. You can't put just a simple control signal in this single equation by observing electrical and mechanical that will solve the problem. Even though it's kind of deceitful, you think you have to just measure locally what is the electrical power and then compensate. You actually can create slow oscillations among different machines. So you don't want to do that. So there are governor controls that try to keep this frequency stable, but it's very much understood that you cannot rely only on those to balance the system. You have to make a lot of decisions so that these are operating close to have these two quantities matched. Okay? So that's the important point. So it's not a controls problem. And control engineers got out of it a long time ago. Okay? And so power systems engineers use all kinds of approximations at different time scales to find practical solution until they say this is no longer a control problem. So we're not going to try to control it like that. We just are not going to try to get out of a kind of narrow region where we can actually analyze, linearize, you name it, right? A narrow region around that point. And by the way, most of the blackouts that happen, they happen because the system has something malfunctioning. There is no global awareness of how to change the set points to go again close to a stable point where the local control can bring you. And what happens is that you create these big oscillations among big generators that eventually lead these generators to disconnect, and there you go, you have a blackout. Okay? So people think that blackouts is because a squirrel cut a line and then the line caused everything. It's actually not like that, right? Oftentimes it's because these systems cannot resynchronize and go around a stable point and create these strange oscillations of power that eventually take them off the network because of safety limits and cause these cascading failures, okay? Okay, so now this is actually a fairly old picture, but it is to show that a lot of the composition of sources for the generation is in fact fossil fuel of some sort. And most of the renewable that we use today is due to hydroelectric power, which is great if you have it, but you may not have it, right? It just depends on whether you are in a place that has a large river, right? If you are not in that place, tough luck, okay? So why do we like them so much? They actually have a very nice property, that these fossil fuels are very dense in energy, right? And subatomic physics is the one that is the densest in energy. So in a very small space, you can produce a lot of energy. So that's really something unique that they have. And you can see it here. This is a Wikipedia table that tells you the energy density of these different materials. It's called storage material because it's sort of saying this is intrinsically what energy they have stored. And you can see that gasoline, diesel is actually great, right? Because you can see how many megajoule per kilogram it has, which is nice. You see that hydrogen also has quite a bit more, right? It's almost twice as much, right? It's even more than twice as much. But the problem of hydrogen, if you look at per liter, it has very little, right? So that's the column that you really want to look at. And look at how lousy is the lithium-ion battery. It's really pretty bad compared to oil, right? And coal is not bad in terms of energy density, is worse than fat and worse than propane, but it's very abundant. Right, so that's the issue there, okay? And so you can also look at other battery types. They really don't compare, and they haven't been scaling up that much, right? But we have electric cars because we can now create arrays of batteries and put a lot of them, right? And then sort of get up to the point that it's comparable to a tank of gas. But what is the tragedy with those guys? Is that, again, the tragedy of the commons, another tragedy of the commons, is the fact that there is, you can burn them, they're fairly concentrated, and they produce waste, which is a gas, which is already in the atmosphere, except it is not in the atmosphere at the concentration that they keep generating, right? So you have CO2, nitrogen, all kinds of pollutants put in the air, and it's dumped, and really, there are some policies to contain it, but that's a reason why it's very popular, because nobody is really paying an adequate amount for the effect. Forget about the short-term effect, the long-term effects, right? If climate change is true and this is causing it, then it's irreparable, right? It's a huge effect. So then there come renewables. Renewables are nice because you pay for the setting up, the transducer that will convert some energy that exists in nature into electrical power. But the problem with these sources, wind in particular, it's quite consistent if you average the amount of energy that wind produces every year, for instance. But if you look at smaller scale, it's one of the ugliest random processes that you can deal with. It has every feature of a random processes that you don't like. It is seasonal, so it's not stationary, right? And it's also fractional. So it doesn't have nice conversion properties on the spectrum and all of this, right? So it doesn't really make it easy for us to predict what they will do. It's still possible to predict short term, but long term, in terms of hours, oftentimes is highly unpredictable. You can have a lot of wind for 3 or 4 hours, right? But you can't be sure it will last 3 hours, right? There are very few locations that have sort of fairly regular wind, and even then, there is a lot of variability. Okay? So really, wind has still a problem, which I think is more from the statistical point of view. How do you account the wind production globally, et cetera, et cetera. It's not because people haven't studied it, but I still do think that there are some analytics that we should improve regarding wind. Solar PV power, this is one of the sources that is not created with a wheel, but is conversion of photons into direct current. And then it would be great to use it as a direct current source, but because we have an AC network and all the appliances are designed for that, we have to use an inverter. Now, one of the myths is that solar power is not that much. It's actually not true. Solar power delivers about a kilowatt of power per meter square. So it's not that little, right? We said that a house could be 10, 40, small house, 10, 40 kilowatts. It's not that small. Now, the problem is efficiency. The cheapest solar panels that you get today are about 15% efficient. These numbers are changing, by the way. The ones that are really nice are 40% efficient, but they're very expensive to produce. So, these are more for applications like satellites or other things, but not really for rooftop solar. So the rooftop solar is on the cheap side, and therefore it wastes a lot of power, but you can produce, 150 to 100 kilowatts per meter square, which is not that bad. But now, just if you make a little bit of a calculation, so 7 kilometers square will give you 150 megawatts of power. 8 kilometers square will give you 150 megawatts. So if you get about 7 kilometers, you get a gigawatt, right? So 7 kilometers in the desert is not a big deal, right? And so especially in Arizona, where I am, is plenty of space to set this up, and this could be as much as a nuclear power plant, okay? 1 gigawatt, okay? Now, obviously, solar power cannot be used for certain applications, right? So you can recharge lithium-ion batteries at home and be great, but this is absolutely not sufficiently dense for transportation, okay? So you can use it in your RV to camp, do dry camping for a little bit, but you cannot turn on the microwave. You cannot do a lot of things. Certainly you cannot dry it, right? So a very efficient car has 20 horsepower, if a car is 400 horsepower, and here you're like if you get 1.3 horsepower per meter square, right? So it won't work for cars. So let me show you what is the classic diagram of a power network. It's this graph, these little arrows. What these arrows are really substation, and they could be connected to a generator. Here you see this G, right? And what this arrow means is that this is going through, it's an injection point. It's called an injection point, where you have current going to a feeder, and you have a certain level of voltage that is maintained here. And typically here you have transformers that bring down the voltage level from the transmission level. And then you have other points that are intermediate points, and all of these nodes of the network, whether they have an arrow, so they go to a feeder of some sort, or they don't have an arrow, like this guy, the guy number 9 up there, they are intermediate nodes. They're just interconnecting multiple lines that are splitting. So all of these are called buses. They call it a bus, okay? And so let me give you here a summary of the equations that I will go through. Some are just talking about the network as a graph. I have to introduce a few definitions. Then I will give you basically what I will call as Ohm's law for the entire network, right? And so these quantities here to the left, this is what you will look at. Current equal admittance times voltage. Typically you write, when you study circuit theory, you write impedance times current equal voltage. But you will see that it's actually much more convenient to write it the other way around, because this matrix, which is the admittance matrix, has actually exactly the same sparsity of this graph. It has zeros where there is no edge, okay? And then I will show you how these, I will give you the relationship that gives you what is the admittance matrix as a function of the admittance of every line. This is the relationship that gives you the balance of power. So you saw before that I have power equal voltage times current. Here the power I will call as S, and I will tell you in a minute why. And this diag means a diagonal matrix. So I take all the currents in every single bus, in every single point here that is going here, and then the voltage from here to ground. And then if I multiply those, I have actually this power vector. And then there is a big simplification that is made to linearize this equation. This matrix B has kind of the same structure as the matrix Y, but it's instead of the admittance of the lines, we use a simplification of that, an approximation of that. And here this would be the actual power, the real power that you send. So this power vector can be written as this matrix B times theta, which we will see is a surrogate for the vector V. These are above all complex quantities, the IB relationship and the power balance relationship, while these are all real quantities. Okay? All right, so just a tiny bit of definitions for graphs. So a graph is represented by a set of nodes and a set of edges. And to express all these matrices is useful to define what is called the incidence matrix. Is a matrix that has a number of rows which is equal to the actual edges that you have on the network, the total number of edges that you have in the network. So it will be the cardinality of that set E. And a number of columns which is equal to the number of nodes or buses, in this case, that you have in the network. And what you do is, if you have an edge between node N and node L, right? So what do? You actually put a 1 in the EL entry and a -1 in the other EN entry. So this represents the edge between N and L. What you do is you flip the sign. And which one you put minus or plus is arbitrary. Either way it works. Instead, if the node K has nothing to do with that edge, you put 0. Okay? And this particular matrix, which is the incidence matrix transpose times the incidence matrix, this is an n by n matrix. N is the number of nodes, right? This is called the graph Laplacian. If you have any interest in graph theory, particular spectral graph theory, this is an extremely important matrix. The eigenvalues of this matrix tell you a lot about the connectivity of the network and other properties of the network. So people that study network science, they kill themselves finding other features through this Laplacian and the eigenvalue decomposition of the Laplacian. Obviously, this is a symmetric matrix. Okay? I'm not going to talk about spectral graph theory. This would be a digression. But the important thing is that this particular matrix, except for the diagonal, has exactly the same sparsity as the adjacency matrix. The adjacency matrix is the matrix that has a 1 if the two nodes are interconnected and 0 otherwise, right? So what this matrix has is exactly the same 1 in the off-diagonal elements, and in the diagonal elements minus 1, and in the diagonal elements, in fact, it has the nodal degree. Okay, so that is said, all you have to remember right now is the M matrix, right? That we have this matrix which is the incidence matrix. Okay, so we had this synopsis of equations, and we had those vectors of coefficients which were all complex. Why do we have complex numbers? Because these AC signals are sinusoid. They're not exactly sinusoid. They are narrowband signals, right? So the omega here is the 60 or 50 hertz carrier, right, around which these AC signals are varying, and they can't be exactly a sinusoid because the amount of power that you require varies, and as that varies, there are two quantities that vary. One is the amplitude of this sinusoid, and the other one is the phase. Okay? So what do? You do exactly the same that you do in communications. So instead of looking at the signal, the modulated signal, you convert it in a complex equivalent baseband signal, right? And it's just a matter of terminology. Power systems engineer, they call this the phasor. We call it the complex envelope or the complex equivalent baseband signal. They are exactly the same thing, okay? And so from now on, when I'm talking about signals, I'm talking about this phasor, which will have the amplitude V of t and this phase, and I will indicate these as Vt and It. Remember, these guys are complex. Okay, so what is the power? The power, the instantaneous power, is voltage times current of the AC signal, right? So if I do all of these multiplications, then I see that the constant term there, right? If I just use my trigonometric identity, the constant term there that multiplies the 1 is V times I cosine of the difference between the angle of the voltage and the angle of the current, okay? So that's the actual power. These are kind of standing waves, but that's the actual power I'm sending, and I'm sending it if this is greater than this in a certain direction versus the other direction. Okay, so if I know the difference of phase between voltage and current, and I know their amplitude, then I know what's the power, and if you compute the phasor for this power, then you see that computing the phasor of the power is easily obtained from the phasors of voltage and current, is V times I conjugate, and now you get a complex number where that term Vi cosine theta V minus theta I is in fact a real part, and the imaginary part instead as sine of theta V minus theta I. Okay? All right. So we call this active power and this reactive power, and this S is called the apparent power, right? And the absolute value of S is called the apparent power, but you only, in terms of paying, what you pay is for the active power. Really, this is what the generators are trying to send you, okay? So this is sort of the diagram of these different things. And why is this useful? Why is it useful to reason in terms of active and reactive power? There is some information that goes into the reactive power. If you have a lot of reactive power, then it's as if your impedances are not matched. So if the reactive power is 0, you have the maximum power transfer. So what power engineers, they cannot match impedances, right? This is not a contained circuit. So what they do is they try to control reactive power by essentially having certain places where they can actually control the phases of the AC signal and reduce the reactive power that way. Okay? But we are not going to talk about reactive power at all, because for the point of view understanding the economics of this, it's actually more important to understand what happens to the active power. So as I said, if we stack all these phasors, sorry, that guy should be I and V, then the equivalent of Ohm's law, this is a basic theorem, is that the vector of currents is equal to the admittance matrix times the voltage. And the reason why I bored you with the definition of the incidence matrix is because the admittance matrix is equal to the incidence matrix times a diagonal matrix that has all of the admittances of every line here, right? So there are as many lines as many are the edges in that graph, times the incidence matrix. And then there is this other term, which is, again, the transpose of the impedance matrix, times what are called shunt impedances. And this comes from the fact that the transmission line has a resistive and inductive effect, but it also has a capacity effect, right? So that shunt line comes from the fact that if you write the equations of an entire transmission line as a two-port system, in general you can utilize this equivalent model where you have resistance, inductance. These are basically the resistance is Rij, and X is the parameters that goes with the susceptance. It's called susceptance with the inductor here. And the capacitive effect is instead represented by this shunt admittance. And in particular, Yi is 1 over Zij. Zij has these two terms. So Yi has a real part, which is equal to this, which is the conductance, obviously, and imaginary part that can be obtained through the susceptance. Okay? And so what this Y vector is the series of all of these parameters for this two ports model that represent the entire transmission line, right? It's a distributed circuit that can be represented itself as a two-port model. So that's how it comes. Okay, and then you can get all the power phasors, the apparent power phasors, through the equations that I said before, that the diagonal, the voltage at every bus times the current conjugate at every bus gives you the power phasor. And then if you substitute this equation here, right, then you can write that the diagonal of the voltage times the product between the admittance matrix and the voltage conjugate will give you the power. So this is the equation, right? So it's V times the sum of all the Y and L conjugate, VL conjugate. The sum, it says here, it's between all buses, but this matrix actually has the same sparsity as I mentioned of the graph. So in effect, only the coefficients that correspond to the direct neighbors of this bus will have a non-zero coefficient. So, and since these graphs are typically very sparse, there are not that many terms here. But what is important is that all of these terms, you have all of these products, VL conjugate Vn, right? I can put Vn here, so you see these are quadratic equations. So this is a nonlinear equation. And these are also instantaneous nonlinear equations. There is another aspect here. I am utilizing this. I have a static vector S, a static vector V, a static vector I, which has a certain phase and a certain current. But initially I told you, well, the absolute value, right, the amplitude and the phase, they do depend on time. So how comes I can write these all in algebraic equations? This should be if the circuit is not changing, these should be convolutions, right? These are differential equations. But the reality is that the signal is very narrowband, right? So you can approximate the relationship that you get as an algebraic equation where this is in fact the frequency response of the transmission line at 60 Hertz or 50 Hertz. That's actually what you do. And so this can become signal of depend on time, so the phasor is changing over time, but it's changing slowly, so you're not really seeing the transients of the transmission line. The transients you worry about are the ones of the swing equations that I was mentioning before. Okay? And these are the key equations for monitoring the grid and for optimizing the grid. And by the way, these are the equations that I was using, if you have a measurement of power, right? If you measure the voltage and the current in a certain site, and you can measure the relative phase of voltage and current locally, right? So then you have a measurement for S. If you have a measurement for S, that was relate S to the voltage, right? And if you can solve those equations, you can solve the equations for V, then you can reconstruct the currents in every place, the powers in every place. So these are the nonlinear equations that I was solving in my decentralized computation problem, right? When I was talking about extracting the state was actually the voltage phasor from the measurement, which was a power measurement, okay? And I just want you to notice that, you know, it's not difficult to locally measure the difference in phase of the sinusoid. You're measuring them in the same place, right? You're measuring voltage and you're measuring current. These are sinusoids, right? Approximately over a certain time. They have a modulation in the phase, but you look at the snapshot, you measure this relative phase, and that's easy. So why are we not measuring directly the voltage phase and the current phase? Because if you have a sinusoid in one place and you have a sinusoid a lot of kilometers away from that place, right? You have to have a fairly good common time reference to understand what is their exact phase. Okay? So this was not available for a long time until the GPS came about and was provided at a very high resolution for civilian uses. So right now, power systems engineers can actually measure directly voltage and current at different buses using a common time reference. But a lot of the sensors that are deployed on the grid don't have this characteristic. They are still power measurements. They are much cheaper to do. And so a lot of the state estimation relies on this type of sensing. This type of sensing, these type of equations are also important to optimize the power flow. Oftentimes, the way power systems engineers look at this is not in terms of real and imaginary part, but rather in polar coordinates, because for them the phase angle is the most important thing. So they write the equation in terms of cosine and sines of the angle, and they get these equations which are even worse, because these are the amplitudes. Here I omitted the two bars, but these are the amplitudes, these are the phases, and what they try to do is this is the constraint. These are the constraints for the amount of the particular relationship between voltage and current, real and reactive power. And then from this, obviously if you have the voltage, you can infer what is the current, and you can ensure that you are not exceeding some thermal limits. Okay? And so B and G are simply the real and imaginary part of this Y matrix. Okay, so most of the times you are concerned, as I said, about active power, because this is really what decides the set points of this generator. And there is, I told you that there is a very coarse approximation, right, in the synopsis of all the equations. So how does that come about? It's not so obvious. It actually relies on some knowledge of what these parameters tend to be. So what happens is that the resistance of the network is actually typically very small, right? So you can neglect this G and L parameter by focusing only on this B and L parameter, which is more significant, and this will be equal to 1 over X and L. The other aspect is that typically the voltage amplitude is fairly constant. This is a requirement, and it's something that is controlled by local controls on the line that try to keep the voltage amplitude at the same level. So this leads to the following simplification. The other aspect is that the phase difference theta n minus theta l, the phase angle difference at two ends of a line, typically is quite small. They tend to be no bigger than 30 degrees, and that even is a lot, right? And depending on the actual difference of phase, you actually have more or less current flowing through the line. So you don't want a lot of current flowing through the line, and therefore you don't have a big phase difference. So if you don't have a big phase difference, what you can do is, okay, so you can neglect the cosine part because G is small. And so you are left only with the sine part, and the sine part, because the angle difference is small, you can replace with the angle difference. And if you do all of this, then what you get is linear equation in theta. So that's the relationship between the power and the phase angles. And you use a surrogate for your phasor, voltage phasor. You say the voltage is constant, right? You actually normalize it to be 1 because you know at what level of voltage you are in the network. You can renormalize everything. This is called per unit. All this normalization is called per unit. So you represent everything at the same voltage level. You say that therefore the voltage amplitude being constant is 1. And all you do is now you focus on this phase angle difference, which is now the state of the grid. And now you have linear equations. Okay? Now to do all of this, you have neglected losses. So you also have neglected what happens from the shunt impedance. And so what happens is that actually this matrix is singular. And it's singular just as the Laplacian of a graph is singular. And the singular vector of this matrix is, in fact, the constant, all one vector. So therefore, if you multiply from the left b times 1, you get 0, which means 1 transpose p is 0. So what does that mean? If you sum all these powers, you get 0. So that's the balance equation. The amount of power you inject is equal to the amount of power you are consuming, right? Now these powers have a sign, right? If you consume, you are sending power somewhere, right? So the phase angle difference is negative or positive. And so that's why these can balance out. And why is that? Because basically what you are doing is you are neglecting losses. As soon as you say that this is small, right, ignore that, you are actually neglecting the losses that you have with it. Okay? So if you have measurements of power and you want to compute the phase angle, you cannot quite do it. You have to assume that you will only calculate relative phase angle. So you fix one of these angles and solve for the rest. Okay, so these are the two important equations. These are called the AC power flow equations. So if you are strong and powerful, you will solve optimizations where you use the constraint, that is the AC power flow constraint. If you are weak and you want to solve easier problems, you use the DC power flow. And these are always a very good entry point to solve system problems. These are sort of your transportation network flow, right, for the grid, right? So these are what constrains and correlates everything that is going on there in terms of demand and supply. So managing and dispatching power is in fact the most complex side of this. That's why they want to issue that price, because they would like to engage the demand in this. And so let me now look at how this control happens. And to understand that, we have to understand two things: the power markets and the control. And these are really embedded together. Okay? And there's one really nice thing about power systems. When I moved and tried to study this area, I thought, this is really old stuff. There is nothing really interesting. But I think the fact that in real time there are markets that are trying to decide, that are embedded in your design. So you're not just amortizing the infrastructure. There are real dollars that flow through the line. Those are calculated in real time. This is actually a fascinating aspect of power systems. Compared to other infrastructure where you typically have a cost which is not computed in real time, even though you have congestion and other things. So why do we use so little renewable power? I hope I will convince you that this is really because it's a market force that is causing this, more so than the fact that it costs too much to produce a solar panel, right? And that's why I think it's important to understand this part for everybody, to have kind of a notion of this. because now all of a sudden politicians in Germany say, well, put solar panels, we give a lot of incentives to put solar panels everywhere, and then all of a sudden you have that the electricity cost triples. It's not because you are paying the solar panels, it's because in real time those solar panels are making it more difficult to dispatch power. So there is a market cost that comes from the day-to-day operations of the system. Okay? So the problem is not energy density, it's uncertainty, because one of the very important features that costs money is to maintain the grid reliable, is to maintain the balance between demand and supply in real time, in spite of the congestion constraints that you have, because those power flow equations, if you want to have arbitrary power everywhere, may jack up the current in certain lines and exceed the thermal constraint. It's really like, you know, putting too many gas in one place, except instead of just stopping traffic there, you just burn the line, right? So you cannot do it, okay? And the problem is that, you know, us as consumers are completely unaware. When you switch on the line, you don't know what congestion is on the grid. You don't have any sense of it. When you take your car, you get out, you see congestion on the street, you change your road. But you are never going to change your decision in terms of electrical power. You don't want to be bothered with that, but you also don't see the congestion, right? You don't have any impact on that. So solar power has another problem. You know, at least in sunny days, solar power is quite predictable, and you have weather predictions, and sometimes they're fairly accurate. But the problem of solar power is that there is this non-coincident peak of power in the morning and in the evening, and that causes problem in terms of what kind of generators can, you know, go up in that period and then suddenly shut down when you have a lot of sun outside. And so that's the real congestion problem, that the electrical power need to be supplied just in time. So if anybody tells you, oh, I have a net zero building, net zero energy building, you have to ask them, but is it net zero power or is net zero energy? Because it's a very different thing. Because if you are absorbing power from the grid at moments of congestion and emitting power when nobody wants it, right, in excess, then you really are not helping so much the equation, okay? Okay, so that's why we want a responsive demand. Now you have a base load generation, and nuclear power plant, coal power plant are really good at it. Gas power plant can do more stuff. They're actually really nice because they can go up and down fast, but nuclear and coal actually are pretty slow. So if you have to have a kind of flat demand to have them. So what you do is, you know, the amount of electric load you require is like these mountains that are above a big amount. So the big amount you cover with the base load generation. And right now you have a little bit of renewables there, but as you can see, with respect to the demand, which is the blue profile, the renewables are not doing what the demand wants, right? So you have to cover everything else with reserves, and the more this difference is uncertain, or you have to go up and down quickly, the more those reserves actually cost, right? Think about what kind of power generation could be really fast. A jet engine, not inexpensive power to produce. So with demand response, what you want to do is you want to shape the demand so that it looks more like the renewables. And then you can put more renewables and decrease the base load. And so here you can use less coal, right? So that's really, aside from the cost of the solar panel and the installation, et cetera, these are the system levels, what demand response is supposed to do. This is why we want the ZigBee in your personal area network to do anything to help climate, or the AMI, or anything, right? That's really what we want to do. We want to shape the demand so that you can follow renewables, so you can put more renewables and have cleaner and cheaper power. So now how do these markets work? For a good portion of the 20th century, actually the utilities were all a monopoly, right? So both from the point of view of retailing electricity as well as producing. So the utility was calling all the shots, was buying, had the generators, and was producing power without a competitive market. Now, these, now, the large vertically integrated utilities were obviously regulated. They were trying to do it as a utility, so they were forced to contain prices, and that was true also for telecommunication infrastructures. But monopolies are well known as being market inefficient. And why? Because they were not really careful in making the best deals. Okay? So what model came about? The idea that came about is that the wires should be still a monopoly, right? The big infrastructure should be still a monopoly, but the generation should not. So anybody can enter in the generation market, and they have to compete to get the customers, okay? But now you have this very complicated balance constraint, so you cannot operate the market having the generator every time instant to talk to the utility, how much do you need, I'll sell it for you at this price, etc., etc. So what you do is you formulate the solution of the competitive market as a big optimization problem, and you solve it numerically, centrally, with a big computer system or a server, and there is an entity that does that. And in the United States, these are called independent system operators. Okay, so they take all the bids from the generators, right? They say, I will produce this many megawatts at this cost. If you want more, I will produce it at this higher cost, and so on and so forth. And I have these constraints. And then the utilities go there and say, I want this amount of power. And this independent system operator finds what is the competitive price, the competitive solution for this market. And this is done in multiple settlements, as we will see. So what makes the cost rise is congestion, right? Because you run out of resources, so you depend on certain generators more than others, so they can jack up the price, right? And the fact that there are poor forecasts. So poor forecast means you cannot buy ahead and make an advantageous contract, right? Because always, if you can make a contract ahead of time, etc., where you are not in a crisis mode, that's much better. So what you have to buy is, you have to buy not power but service. You have to say, you have to stand online if I need more or if I need less to do an action. And so you buy these services that are not really just the amount of power, but the service to be there to compensate for shortfalls or for excess power. And I have to say that in many cases still it is regulated as a monopoly, so all of these market considerations don't apply, but even a monopoly has an interest as a cost of fuel, so has an interest in optimizing the portfolio of supply that it utilizes of its own fleet of generators, because the fuel cost is different. Okay, so what does a competitive market do? The competitive market is an ideal model where there are infinite suppliers and infinite customers, and this is sort of the average price-supply curve, right? So depending on the price, you have a certain quantity, and for whatever reason, economists tend to represent everything upside down, right? So they tend to represent the price versus quantity instead of quantity versus price, which will seem more natural, I think, to an electrical engineer. Same thing, sorry, this is a supply curve, these are the customers, they have a demand curve, so they buy lower quantities if the price is high, and they buy higher quantities if the price is low, right? So that's the idea, okay? And a competitive market leads naturally to this equilibrium point. So if there is no supplier that has market power, because it's not the biggest supplier and everybody else is a midget that cannot compete, right? What happens is that everybody will trade until they reach this equilibrium point, which is exactly the intersection between the supply curve and the price demand curve, okay? And why is that? Because they bounce back and forth. Of course, customers cannot buy all they want, so they buy until they are willing to pay, and the generators have to lower the price. So there are price oscillations until you reach equilibrium. And now this you will have to do, if you just let the market freely operate, you will have to do in real time. So that's why you don't want to do it in real time, you want to write it as an optimization. Now, what is the market clearing price? The market clearing price is the amount of money that you have to pay for any extra unit of the commodity you're buying, so in this case power, right? So it will be the derivative of the cost with respect to the generation, okay? So these curves that I showed before, you can, the supply curve and the demand curve, you can calculate for the supplier if you take the marginal cost, so the derivative of the cost with respect to the generation. So this would be the cost of the fuel, right? And for the demand, you have to assume that there is a utility, that you can monetize the commodity, or you have a value that corresponds to the commodity you are buying, and so you take the marginal price, okay? So when you think about smart pricing or real-time pricing of electricity, really it comes from this notion that you have somehow evaluated what is the price-demand curve for your customers. And this is really nice, a nice solution. This is what Adam Smith found, this study, this competitive market. He said this is the natural price because it's the highest price can be squeezed out of the buyers and the lowest that the seller can afford, right? And everything else you are assuming that the revenues and the expenses are matching up, okay? So you can actually obtain this price solving an optimization. You just say, you set the Lagrangian as follows. Right? Suppose that the demand and supply of electricity has to be in balance. That means that all the sum of Li, which is your load of electric power, has to be equal to the sum of all the generation power, right? So that's your constraint, and lambda is the Lagrange multiplier. And then your objective is to minimize the cost and this utility, right? Or maximize the utility minus the cost, right? You can either or look at a minimization or a maximization. So interestingly, the optimality conditions are such that the Lagrange multiplier is exactly equal to the marginal cost and the marginal utility, right? So they have to be the same, and that's exactly the equilibrium point that we talked about. So that means that you can calculate the Lagrange multiplier of this optimization and use it as a price, right? You don't have to have the market work, right? You just solve this optimization, get the value of the Lagrange multiplier, and pass it as your marginal price. And that's what essentially the independent system operator does, except it doesn't solve exactly this problem. As I will say, it solves a different problem. In its simplest form, this is called the economic dispatch. It solves a problem where, as you can see, the utility for the consumers has disappeared. So it's just simply trying to minimize cost under this constraint of balancing in power. Why? Because the utilities are not giving any option. The demand of power is completely inelastic, right? We switch when we want, we don't know anything, right? So the equilibrium point becomes simply the point at which the supplier can provide an inelastic demand. Okay? All right. So now here I didn't put any constraint, but typically these curves don't last forever. You cannot generate more than the capacity of your plant, and you're not going to open your plant unless you have to produce at least a minimum energy. So there are constraints on the amount of generation you can actually have. So you will max out the cheapest generators, and then you will go to the next unit, and then you will go to the next unit until you fulfill all the demand. So actually then what is the price? The price is going to be the marginal cost of the most expensive unit you had to use. And that will be applied to every generator, even though they said they were willing to sell you the product at a lower price. You actually will apply it to them as well. Which means that generators are incentivized also to be honest and tell you their cost, because they want to be, in any case, chosen, right, to produce the power. And then, in any case, if there is an expensive unit that you will need to utilize because they maxed out all the cheap units, that they're going to be paid at that marginal price, at that marginal cost. So next we are going to be more precise on what they do, because obviously I showed you this AC and DC power flow, and here they are gone. I'm only looking at the balance constraint. So now we are talking about bulk power market. So that means that we are at one of these injection points. That means that we are scheduling hundreds of megawatts, right? We are not worrying about the amount of power that goes in your house, even though we are talking about pricing each individual house. The operation model which is in place right now since the 90s in the United States is making decision on how much power should go in a certain substation, but more importantly, at what price. And this price depends on the different location, because all these constraints that I mentioned before, they have to do with the balance and the losses of power throughout the network take place. Now, are they doing this every instant of time? The answer is no, right? They have to get all this information for this very large area. So they make decisions at different stages. And so in each decision they have more uncertainty, so they try to make decisions based on what is the best guess at that point in time about what is requested. And these decisions are binding, so they have to buy whatever they said they would buy at that point. So very important is what is decided on the day ahead. So that's as lowest time scale. So all the generators offer a certain bid. The utility goes to the ISO and says, I need these megawatts tomorrow, that's my forecast, and the market is settled here. But then during the day they have to adjust all of these. They have in the day ahead decided what are the type of reserves that they are going to have aligned to do it, but then they have to pay them not only to be online, but for whatever power or whatever service they do deliver. Okay? So they actually make those decisions, and they make them at a relatively fast pace. And this is where really demand response is useful, and is kind of aligned to the time frame which you actually can kind of predict what the wind and solar will do, which is during the day, which can go, which can run from minutes to a few hours to seconds. And there are other time scales in which local controls are put in place, so you sense and you do some feedback control locally. Okay? So these are the famous specifications, right? Communication engineers want latency specifications. And if you read these specifications for what is the common substation automation standard, they are actually pretty demanding. You see that the transfer time for a certain class, the TT6, is 3 milliseconds. That's very little. Are we going to do across the United States in 3 milliseconds? I don't think so, right? But there are others that are much slower, right? The fact that you want to put data here in a historian, right? You can wait for seconds, more than seconds. Then events and alarm, you also want to send in seconds. And then operator commands, you will want to send in half a second. Okay? So I would say that you can consider any control of demand response. You want to generate a certain aggregate response for a lot of loads at the substation level, then I would say half a second is a reasonable demand for that week, right? So that's pretty fast, right? And this is why I told you this is a pretty demanding area, right? right? It's not just my device talking to the home energy management system, right? But it's also covering the distance that is needed to coordinate what you will see at each substation. So this is the multi-settlement structure. So you have these different optimization stages, and this is what happens in the day ahead. You have the security constraint duty commitment, right? Stage, and I will tell you what this does. Then during the day, real time, you have adjustments. You have hour ahead adjustments and then real time adjustments, and these can happen in 5 to 10 minutes, right? And in all of these adjustments, you are essentially buying some of the services that you acquire from the reserves. So you may want to give instruction for the demand response, or you buy resources from the response to operate at a much faster level in real time, but without cleaning any other market. Okay? And then what you do at a slower scale is essentially balancing. So you bought resources that can balance in real time, but you are not trying to make the action which is most economic. You just do the action, period. So what you bought is essentially the cheapest contract to make that action. Any action in a set, and then the one that you pick in that set is not necessarily the most economic. And these are the things, this is the nomenclature that happens in this sort of very short-term control. There are all these levels of control. There is the primary control, which is purely local. These are all intended to control the frequency so that you don't have these big shafts moving around too fast of a frequency or too slow a frequency. Then you take over with secondary control, and this actually is done over a wide area, okay? And then once you do actions of those kinds, you're not necessarily balancing the most economic point, so you engage the tertiary control that is trying to rebalance things in a way that is more economic, and this is obviously slower. So the more you go this way, the faster you need to be. So the primary control is really more of a local problem of the local governor controls of these generators. While where the demand response can actually take place is really to provide these two, right? Rebalancing of overall amount of power that needs to be bought, but also provide some fast services to toggle up and down to respond to some faster variations. And these are essentially the frequencies. Now, if you don't do frequency response, in fact, these instructions are sent, let's say, one every 10 minutes, right? But so then why did I tell you that you need half a second? You need half a second because the response time matters. So even if you don't receive a lot of instructions, you want after the instruction to react with a certain time. And that characterizes you as a better reserve than others because you can go up and down very quickly. And so you have this fast ramping ability. So that's the decision space. You have in space, you're trying to be below the capacity limits of whatever generation you have and the thermal limits of the line, right? We're trying to balance the amount of supply of power, the red wiggle with the amount of required power, which is the blue wiggle. But you also have to ensure that this instantaneously holds. And do you have any constraint in time? Actually, you do. Those equations, the swing equation, they do provide a constraint. You have what is called a ramping constraint. So these big generators, they cannot inject any kind of mechanical power, right, to compensate and ramp up and down the power. So this provides constraints that actually are operating in the time dimension, in that plane. And so when you look at a certain horizon, you not only have to consider the power balance constraints, the transmission line constraints, but you also have to consider the capacity constraint and the ramping constraint of your network. And as we said, if the demand is inflexible, you only have to minimize cost. And again, what you're trying to optimize is the amount of power and the price that goes to a certain substation. There is, in the classic framework, no control, no demand response, nothing in the distribution circuit. Once you have that power decided and you think that this little substation or big substation requires that amount of power, there is no control that takes place. Okay? So here I'm just taking a snapshot to come and define what are all these acronyms. One of the acronyms that is a classic optimization that you perform in power system is the so-called optimal power flow. So this is not looking at the ramping constraint, it's assuming that you have units that can survive the ramping, and you are trying to understand in real time what is the minimum cost for that particular time instant that will satisfy the balance constraint, the thermal constraints, and the capacity constraint. And if you want to include the ramping, it's just the ramping from the previous time instant. You don't look in the future, you're just myopic. You know how much you produced the previous time instant, you just are trying to not make those units go up more than they can in this time instant you're making the decision. Okay? And obviously the decisions are made between time t minus 1 and time t. This is not continuous time. You are just trying to do it in different epochs where things are pretty constant or on average quantities. So this is called the optimal power flow problem. And I said, even if you don't want a market, this is something that even monopolistic utilities have to solve because they have different costs of fuels. So they try to minimize the cost. And here, how does the graph come into the picture? There is a set of buses, which I call G, which is a subset of all the buses that are in the network where there are generators attached. There are buses where there is demand attached. This is the complex power that is generated at a certain bus I in this set. And this is the cost that is associated with a particular generator. And these costs are typically convex, they grow, so the more you ask the unit to produce, the more it will want to be paid to produce that. So that's how all of the full problem appears. So you try to minimize cost over all of the units that you have available, satisfying these constraints that you have on the capacity, making sure that you have the power that a load bus is injecting is equal to the demand that was given to you as an input from your forecast. Here are these AC power flow constraints that include the network constraint and is also power balance, right? Because you are balancing the demand with losses. And then you have other constraints. You don't want the voltage amplitude to exceed certain limits. And you also have power flow constraints. You don't want that the power that flows over a line exceeds a certain limit. And the optimization variables that you have are the amplitude of the voltages and the complex powers and the currents over the lines and the power flow over the line. Okay? Now this seems pretty benign, but there are two reasons why it's not that benign. It's because these constraints are unfortunately non-convex, and also because these networks are pretty huge, 50,000 buses, right? So this is not this is a big non-convex problem to solve. So a lot of optimization people are obsessed with this stuff. So there is a portion of people in operation research that really is interested in power system because of the complexity of solving the equations. In many cases, what you solve for is the DC version of this, where you replace this with the DC power flow approximation. You replace the power flow constraints with limiting the angle difference over the line, and you use the slack bus constraint. This is because these are As I said, these are non-invertible equations, so if you fix one of the angles, then you can ensure that the relative angles in any case are met, right? Because they are all different up to the constant. And so then you solve this problem, okay? Obviously, you know, the price that you pay for that is that this is not inexact, right? You have a certain error, so you're not truly minimizing cost, and you're not truly taking into account the thermal constraints properly, okay? So who should generate those? So here, this fleet is decided, this set G is decided. Do you need all the generators you have? What do you think? The answer is no, because the summer you need more in California, right, than you need in the winter. So you typically have excess, right? You have generators in excess of what you're actually going to use that day. So you're actually able to also choose who you're going to use. And generators, for that, they give you sort of a flat cost for just turning them on, okay? And they want the ISO to decide which one of them should be turned on, and then the bid appears to characterize how expensive they are, okay? So today, because we don't have a lot of renewable, the demand is actually quite predictable, and so this is very effective. So the day ahead, these units are committed, and the mistake that is made is not that large. So what is traded in the real-time market is not a huge portion, 5–10% of the bulk amount that was bought the day ahead. And the idea is that you commit units and also you commit reserves. And you commit reserves doing, looking at contingencies. Contingencies is the loss of a generation or a transmission line. So you account for all individual contingency that can happen, and you have to have a plan to have enough units and enough reserves in case one of the systems fails. Now, you should, in principle, consider 2 to the n possibilities, but that's combinatorially intractable. So you only are prepared for one contingency at a time. That's called the n-1 rule. Okay, so I think I said this in words. So obviously you cannot do this instantaneously, so you discretize different points in time, trying to discretize the load profile. You sample the load profile, and you try to decide which unit you're going to use throughout the day, in the day ahead. And so here you still have the cost, right? The objective is the cost of generation. But you also have this I, which is the integer variable that is telling you whether the unit should be on or off. So the I variable over there is 0 or 1, okay? And the cost depends on the 0–1 variable because there is a flat cost for turning it on. Now obviously if it is off, then there is no cost in generation because you're not producing anything, okay? And that's shown here, right? If you see what are the capacity limits for generation I are these two limits, right? You don't want to produce less than this, and you don't want to produce more than this. But if the unit is not on, this is 0, 0, that means this is 0, so this becomes an irrelevant constraint, okay? And typically the way this is solved is without looking at thermal constraints, doing a simple balance constraint that you see there is the hourly balance constraint, and here you account for the startup cost, and you also have ramping constraints, so the unit cannot have a finite difference between these generators level, which is bigger than this. There are other constraints to make your life more miserable, which is that these units have to be on for a certain amount of time if you turn them on, and if you turn them off, they have to be off for a certain amount of time. So these are called the on and off constraints. So you have to add this integer variable for a certain amount of time. You have to make sure that they're greater than t on time and t off time. Okay? So after all of these, the way this appears is everything here is linear, right? Because we removed the AC power flow constraints, and therefore this is a mixed integer linear problem. Okay? For the security constraint unit commitment, what you're adding is also the cost of reserves, right? So you have an additional cost of reserves, and you are looking at all possible contingencies which are in the set S. So the set S is telling you that you will have a certain load in that case and a certain amount of generation in that case due to the contingency. The contingency could be also that you lose, that you have a blackout in an area because of malfunction or something. So you also don't want to lose a lot of demand of power, because everything, remember, has to be in balance. So if you start losing a lot of power, then the generator frequency increases and things go haywire, right? So you want to have everything in balance. So these are all the contingencies, S and the index of contingencies. So for every possible contingency, you have a different constraint. The reserves have to be able to cover all of these. So basically, the reserve that you engage in every different situation has to be less than the reserve you pay for, right? This is the capacity of that reserve, right? But you are not going to utilize these all. You're going to utilize whatever the contingency requires, okay? And now you can commit not only the reserves, but you can also you can commit different units depending on how costly is the reserve. Okay, so now I didn't talk about renewable generation. So do you think that the renewable generator sources go in the day-ahead market, offer a bid, and make money out of that? They don't, because they can't forecast what they can give, right? So these are contracts. So if these generators fail to produce what they, by contract, were forced to produce, they have to pay a pretty big fine, which is not a small chance for a wind farm. They cannot tell you exactly at what hour they can produce power than the next day, right? So they forego this bidding process. And is this bad for them or good for them? It's not that bad in one way, because they get paid at the marginal price of power. So even if they didn't participate, right, they get paid the same amount that the ISO decided would pay anyway, okay? But there is a little bit of a problem there, because since all these bulk decisions were made with these fossil fuel generators, there is very little that they have to cover, right? So they always, oftentimes, if you overdevelop them, they are in excess. And this is not no joke, it's not funny. What are you going to do? You're going to turn off the wind farm, right? So that's really why we don't use a lot of them, and why people say, oh, there's renewables, you know, they threaten the stability of the system, they are riding on these incentives. Part of the incentive is that they get paid by marginal price, but the drawback is that this is not really a model that we can sustain. Okay, so what we schedule is effectively not demand, but net demand. Okay, so now let me utilize really very simple probability theory to explain to you this problem from another perspective. Okay, so what are these ellipsoid and circles? So let's pretend that the load in time t1 and time t2 is correlated, and these are jointly Gaussian random variables. So these could be, you know, the level curve of the joint probability. Okay? So what are these different level curves showing? Here is showing that at time t1 and at time t2, this value is positively correlated. So if this is high, the next time instant has high demand, and if this is low, the next time instant has low demand. This is the opposite, right? If this is high, the next time instant this tends to go down, and if this is low, it tends to go up, right? So that's a negative correlated. And here, these are not correlated, so I can't predict this at all, right? So what I'm trying to do with generation and reserves, I'm trying to find the load in whatever is feasible, right? So how do I look at the ramping and generation constraint? The capacity constraint tells me that this generation here and this generation here has to be in a box, right? And the ramping constraint is bounding the difference, right? So effectively, depending on what are the bounding constraints, I am forced to be in this pink area. I cannot be in the box, I'm in this narrow area, okay? And in this feasible set, I have to fit all the possible loads that can happen in that period, right? And so if the load is predictable and kind of flat, that's easy, right? If the load is unpredictable, that's not so easy, right? It can get out if the ramping is small. And it's especially bad when it is predictable but it's not going, it's ramping a lot in the wrong direction. It's not flat, right? So what we don't like is both unpredictability and variability. And that's exactly what wind and solar do. The solar power does this to the net demand in the morning and in the late afternoon. It makes it go up and down in a way which is contrary to make it flat, right? So you have these big ramps from up to down in the morning when the solar power kicks in, and before everybody is going, is getting out of the house and going to work, right? And in the evening when everybody goes home, turns on the lights, and so on and so forth. So capacity is basically wasted on variable demand. It's ramping what you need. And that ramping is provided mostly by reserves, which are more expensive. Okay? So if you can flatten the demand, essentially what you can do is you can shift this ellipsoid again inside the region, right? And so there is a way of dealing with variable demand that doesn't require a lot of real-time communications, which is you have tariffs that change over a certain time, right? If that's predictable that you're going to have that, you give economic incentives that are regularly given. They say, in the morning at 8 a.m. you have this very high thing, so then you don't need very fast communications to do that. You can communicate it even months ahead. But if it starts being unpredictable, right? So if you have this random renewable generation, then that guy somehow has to be accounted for when you look at the generation. So when you look at what is feasible with a renewable and a generator, so you will want to not look at that as an inflexible resource. So there are two open problems to a certain extent. Nobody has truly understood how to make this economically viable, right? And this idea of demand response is still not completely fully fleshed out, precisely because the control framework hasn't been fleshed out. But the overall goal is pretty clear. It's pretty clear that you have to add two random variables. These are the renewables, these are the demand. They're in opposite sides because the demand is drawing power, the renewables are generating power. But if you add these two random processes, then you get something which is a bigger ellipse. So you have bigger uncertainty, right? And simply that's determined by the fact that if these are two independent processes, then the covariance of these two will be the sum of the covariance, and basically the area of the ellipsoid depends on the determinant of the sum of the two matrices, which is greater than the sum of the two determinants. So overall, this area is bigger, so you have more uncertainty. And so now you need to cover this uncertainty, and again, capacity, which is what you have from nuclear power plant, big coal power plants, is wasted. All you need is more ramping. So you need more fast ramping reserves, which are more expensive. Okay? So, I mean, it's inevitable that if you produce more renewables than what power you need, you will have to shed them, right? You have to just disconnect them. But what you're trying to do is, again, with demand response, to rebring everything inside that in spite of the uncertainty, right? Because you have some flexibility in doing that. But as you notice here, why do I look at two-time instance? Because what people tend to forget if they focus just on OPF, cost, one instant of time, is that there are intertemporal constraints, right? So if I can delay my dishwasher, right, I eventually will have to turn on the dishwasher, right? So I cannot see an instantaneous drop of power. I have to account for the fact that eventually I have to turn it on. So those are intertemporal constraints that need to be accounted for. And the idea in the smart grid vision is that somehow you will have an aggregator, right, or the utility itself that will monitor your consumption, will somehow understand how these shapes that you have in the house move. Maybe will understand that you are taking a shower here, that this is your dishwasher, and so on and so forth. So we'll do its own data analytics and calculate this magical price so that this will have the shape that the aggregator wants, right? And so that's the vision. So I hope that now you understand why this entity wants to do that and what are the challenges. So then the home energy management systems, they can also solve a minimum cost problem, right? They have their own price, they have certain intertemporal constraints, they have to solve a minimum cost problem over a certain horizon, considering whatever are the constraints, which here I represent with that set lambda n, and potentially deadlines for doing what they want. And there are all kinds of tricks to decentralize these optimization, which I won't talk about because I think you would die on me, but this is something you could solve in a decentralized fashion. The simplest way of doing it is called primal dual decomposition, where everyone is given basically a price from a certain controller, which is a Lagrange multiplier effectively, and then since this Lagrange multiplier down, the nodes locally check what would be the minimum weighted cost with that Lagrange multiplier taken as a price, and then they send back what they want, right? And the central optimizer recalculate the price and so on and so forth. Okay? So that is one way of decentralizing, or you can actually use a version of the multi-agent protocols that I mentioned, so then you don't need to send all of your demands to a central place. You actually solve these in a fully decentralized fashion. So basically your homes are talking and figuring that out from a, okay? And so this, in this case, if you look at this, this could be done, but this cost itself is something that has to emerge from the grid and from the expected response of this, right? So what are the issue with this? I was kind of laughing, right? You are selling a negative amount with respect to what? With respect to a baseline. So the idea is that the utilities or the aggregator will measure this baseline when you are not responding, right? And say, this is what you want. And then they will use that as a baseline to pricing your megawatts, right? So effectively, what you are paid for is for not consuming, for not doing a certain thing. And now this is not the reason why this was blocked, but actually this was advocated by utilities, but there was a pretty bad precedent. Because FED, which is this federal organization, made an order saying this is a great thing, the best thing since sliced bread, but the court blocked it. And the court didn't block it because it was strange in terms of asking somebody to be paid for not doing an action or not taking the shower or whatever. But it was blocked because the utilities were trying to make money twice, right? They were trying to make money because they were selling stuff to the customers, and then they were selling this to the market, and it didn't make sense, right? So they couldn't be at the two sides of the equation, selling not action, right, to the market. And so that was blocked. It was challenged, it was blocked. And it was a bad thing for demand response in general, because the utilities were all focused on doing that, and then the court suddenly said, no, this makes no sense. You cannot make money from the customers and then make money from the market wearing two hats. It doesn't make any sense. There is another problem in all this pricing, right? That you have to learn the demand price function, right? So you do not have the demand price function, you're going to make mistake. Now you have suddenly a closed loop also from the system. So if you make a mistake in predicting what the demand will do, since all your actions have a certain latency, you can destabilize actually the whole system. Okay, so it's not trivial to calculate the price reliably. So that is the idea. The idea is that this will be the interface, and designing this market interface is actually not trivial. Okay, so well, do we have any other alternative? You know, we have to find some way of separating, shielding the ISO from micromanaging your house, right? So at this level, we cannot make microscopic decision here. So we have to have a level of abstraction that allows the ISO to see some kind of resource that is available. It doesn't necessarily have to be a negative generator, but it has to be some kind of resource. So there is the challenge of dealing with heterogeneity, the challenge of having a lot of control knobs, and the challenge of modeling how they will respond in the market without going to the level of detail of the constraints of each appliance. So what I suggested in my studies, and this is not just my idea, is to essentially try to find an aggregate model of how the load responds to a certain class of appliances. They are not all the same. So if you have a baseline model for your water heater, for your air conditioner, right? So even though they are not exactly having the same parameters, they're not from the same producer, they roughly have the same kind of inner working. So if you can classify, you can look at those equations that characterize how those consume power for a certain comfort temperature that you want to maintain in the house. Then you can essentially quantize this population. You can say, okay, you are in this class, then you behave according to this model, right? So all of these devices have a response to my answer, which is the same. And so then you only have to know what is the volume of those devices and in what state do they find themselves. And so that's how you can essentially schedule this. And pretty much how we schedule services in the internet, you know what the quality of service request is here, so you actually are able to deal with the requests and provide service. Okay? And there is another advantage of this, is that if you rely only on an interface towards the house, it doesn't discriminate anything. What are you going to do when things move, right? So electric vehicle is the perfect example, right? Where you have mobility, so you will want to have an interface that follows this thing around. Also, you have many other applications which you don't want to utilize exactly the same model potentially. One of these is server farms, where you try to ship information from one server farm to the other. And you could do it in response to power shortages, because these server farms actually have a very strict limit on the amount of power that doesn't allow them to turn on every server at the same time, right? So they actually need occasionally to ship information elsewhere. So this is the general service model, right? And I'm almost reaching an end. The general service model is that you have these devices basically have a particular description of the job that they do. Like the simplest state space description is for a load which is deferrable, your dishwasher. So your dishwasher has a state which is either on or off. And when it's on, you cannot interrupt the dishwasher or your washing machine, right? So you will have a certain load profile that depends on the cycle it needs to run. Okay? So just find an approximation of the shape of the load profile, right? And put together all of the appliances that have a similar load profile, right? And then all you need to know is when that appliance essentially is available for the system to be deferred, right? So I want that service. I want to wash my dishes, but I don't need to wash them now. So that defines an arrival process, right? If this is an object that instead of just being on and off has a more complicated state, for instance, a battery would have a certain level of charge, then you have to split this arrival process for each of the particular state of charges that you have, which you will again quantize. And so then you can define a certain number of controllable loads that arrive in a certain class Q in a certain state X. Okay? And so what do you have to track? Well, you have to track not only what arrives, but what do you have in a certain state. If you have a certain number of deferrable loads, then you want to activate some of them to change the load profile at a certain time, right? And so you can resort to this, and this is going to be essentially their current state at time t multiplied by this delta function that is just selecting what you had arriving in that place. So what does this amount depend on, right? What is the amount that you have here dependent on? Is dependent on how you control them. And the way you control them is essentially shifting their state. So you go from a state x prime to another state x. For instance, for a battery, you are charging the battery, so you were originally in a certain level of charge, and then you charge them more, so you move them, right? If you are discharging the battery or doing V equal to the grid, then you move them to a lower charge, and so on and so forth, right? So there is this signal that tells you the number of appliances that moved from x to x prime, and instead of using those that move in that time distance, I'm going to use a sort of staircase signal that tells me whatever moved before time t. And I'll make it clear why I prefer to do that. Obviously, if you take the finite difference of that, then you have the number of appliances that moved in that interval. Okay? So if I use this, then I have simple linear dynamics that tell me the state of occupancy, right? So it's the arrival plus the ones that moved to x minus the ones that moved away from x, right? So that's very simple. And then the important thing is that typically for all of the appliances that are of interest, I can always describe the association between the quantities that I move and the actual demand of electric load through essentially something which is proportional to this change of state. Okay? So now I have a simple linear dynamical model that tells me how to do that. And what I've effectively done through this model by clustering all these appliances in these different classes, I've solved actually a fairly complicated problem, which is to understand what is the feasible region for a load signal, L of t, which is the sum of two signals which are individually constrained in that set L1 and L2. So basically you have a vector of two signals. They have to lie in a certain Cartesian product, but I'm not interested in the pair. I'm interested in what are the sum, right? This is the sum load. And so this doing this operation is called doing the Minkowski sum of these feasible sets, right? But in fact, it's not that difficult because in fact, what is feasible is just something that limits this amount that can ship in and out of the system. And the communication to this is actually fairly simple, right? Because say that I decide that I want to move, and here I'm omitting the state, I want to move a certain number of appliances to change state. So in this case, let's say that there is only one signal because I want to turn them from off to on. Okay? So these are deferrable appliances. They have a certain load profile. And I decided that since I need to move a certain number at a certain time, T naught, from one level to another. So what do I do? All I have to dispatch, since I know the aggregate arrival, is the timestamp at which the arrival was equal to the number I want to dispatch right now, right? I can't dispatch anything which is beyond what is in the system, okay? So if I broadcast this message to everybody, they know when they arrive, right? So that they can switch on, okay? So I don't have to communicate individually, you have to do it, or you have to do it, or you have to do it. I actually can control it pretty easily. And this is true for deferrable appliances. For general appliances like thermostatically controlled loads, it's slightly more complicated. I have to provide a table with a percentage I want to move in a certain class and in a certain state, and I have to randomize this protocol and hope that the scale is big enough that the answer I receive is correct. There is actually another advantage of this, as I said, that I can be differentially private, in the sense that all I need is actually a survey result. I actually don't need to know who arrived here, if this is from the household here in Albuquerque, or it's in Las Cruces, which is a place nearby, right? And so that's useful because I can apply this notion of differential privacy, which is essentially a notion that allows you to hide who is in a particular class, who is the responding to a certain feature that you're querying for in a database. And the way this is done is that occasionally I am just gonna flip a coin and not respond to the survey, not say, not do the action that is required, and in general the centralized operator that only sees the results of the survey, how many are in that state, won't be able to tell who did that action. So I cannot predict really who is in that group. Okay, so now that's the difference of this, is that now I can arrive in the system. But why would I arrive in the system? Why I would let you know that my dishwasher doesn't have to operate immediately, right? I need economic incentives. So here is the difference between sending a pricing signal and sending an economic incentive that says if you can delay your dishwasher by 2 hours, I will give you this discount. So there is this difference between these two models. That if you have to send a price signal, what you are trying to do is to control together the intertemporal load shifting decision and the consumption level decision, right? You are trying with the price signal to control both of them, but you don't know exactly how those two interact. While in the other scheme, what I'm going to give you is essentially an incentive to participate to the survey, to tell me that you are willing to take the discount, right? And so now at this point, I will do with whatever is feasible, whatever I want, right? Because it's a contract. My contract is I can delay by 3 hours if I want your dishwasher. But you are not deciding based on the price that you're going to delay by 3 hours. I decided. You just told me I'm willing to take the discount. I don't want to delay more than 3 hours. Okay? So that's a very different model because you have much more under control. You control the entire physical set of action. In both cases, you're not harnessing the full feasible set because people are not going to tell you exactly how flexible they are, right? And if they receive a price, there is also an imperfection in that model that will not allow you to control exactly what they will do. But the goal is approximating the physical set. And I hope that at this point you understood that the idea is that the wholesale market values reserves already, has a price that is willing to pay for reserves. So based on that, the aggregator can provide incentives because it can calculate what amount of a certain type of load it will need to construct a reserve for the market that can deliver those certain features. Okay? And by doing that, so how would that price be calculated? It would be calculated just as generators calculate their bids. They want to understand whether they're going to make money, right? So it has to calculate what discount it can give you so that enough people will participate, right? But by the same token, they will make a profit by selling this flexibility in the market. And so we have done some work in how you would actually close this calculation. And what happens is here that at this point, if your incentive is C, right, then what happens is that your arrival process depends on the incentive, but then the aggregator has all the feasible set of actions available. And this feasible set of actions is over different classes V of load, so you will price them differently. So you don't price apples and oranges the same way. If oranges are more precious, right? If electric vehicles are more precious than dishwashers, you buy more, you give more incentives to electric vehicles than dishwashers. And so that is really what I was referring to when I showed you this picture. This picture comes from thinking about how these will work end to end and provide the type of reliability that is required. And as I said, in terms of requirement, I really very much kind of ran to it, but all it requires is really to communicate this table, right, where you communicate to this population what percentage you will want to meet. That becomes a probability. These guys flip a coin and decide what to do, literally, right? And by the law of large number, you're going to get a number which is close to that percentage. In the case of deferrable appliances, you can broadcast the timestamp, as I said. That's even easier. So what is the range of these messages? What is sort of the range of bits that you need for these messages? If you look at, for instance, an electric vehicle that is telling you how much slack in terms of charging it has, and you are quantizing, saying that there are 200 charge state, 300 slack state. By the way, these are really very fine quantization for the purpose of controlling accurately load. And you assume that for each state there are only two possible actions, so you can go only from one state to the next. Then you will have roughly 120 kilobytes per message. But these 120 kilobytes are not going peer-to-peer. It's a broadcast message, right? So it's actually fairly easy to send. Plus, in these, I didn't account the fact that these typically are very sparse messages, so they could actually be compressed fairly easy. Okay. And so what could you do with that? So I use this model because now I have an aggregate model, right? And for particularly here, I use an aggregate model for thermostatically controlled loads. And in the case of thermostatically controlled loads, my model captures essentially all of these thermostatically controlled loads as some sort of battery that is trying to compensate for the thermal energy leakage that I have because I have a certain difference between the indoor temperature and the outdoor temperature. So what I'm trying to keep is these two temperatures at a certain difference just to have comfort inside the house. So I utilize a bunch of surveys and the temperature taken at all these 6 regions in California. And then you can go to the California ISO database and get the total load that California consumed on that particular day. And now with my aggregate model and surveys that tell me that these are the kind of more common air conditioners in the house, and these are the more common set points for these houses, what I was able to do is I was able, assuming those are perfectly inflexible, to take those slices that account for the different clusters of air conditioners and what is the electric power that they consume, the average energy per unit of time, which is in this case hour, that they consumed during that period. So I use the temperature essentially to infer those, right? So I was able to sort of separate this signal from the rest of the load. And the rest that you see here is load from other sources that are not air conditioners. Okay, so the red line is the total load. So why was this interesting? Because now I know roughly how many are in a class, right? And if I know how many are in a class, I can tell you how much reserve I have, right? And so here I had a target of saying that 4% of the total consumption in California could be my target capacity for the reserve. And remarkably, at least in July, you actually can offer throughout the day that amount which is in the hundreds of megawatts. And in the peak hour, when there is most consumption, you could actually go down by 3 gigawatts. So 3 nuclear power plants, right? And you could do that remarkably without the customer even noticing, right? Because you are maintaining a fairly close performance target, which is to have no more than a certain energy leakage, so no more than a certain deviation from the temperature setting of the indoor house. So this is, I think, is remarkable, and is also a byproduct of having a model that can capture what these particular loads can do, is that you can sort of reverse engineer and find what slices are pertinent and how you will change the equation entirely, how you will flatten the load today, right? This is not electric vehicles. This you will do today, okay? So I have another part of this talk, but I think I'm running out of time, right? When do I finish?
You're done at 4.
At 4. So I have an hour, so I can talk about this a little bit. If anybody wants a bio break, I would say we should stop 5 minutes. This is not very long.
It is actually 3:57. So you have 3 minutes.
Oh, I have 3 minutes. Oh, sorry, I didn't fix my clock. Okay, so this you will find in the slides. It's a brief introduction to some of the horrors that can happen if you don't secure these networks. And I think people are very sort of not concerned about security as much as they should of this network. Now, of course, authentication is very important. You have to put passwords, you have to possibly encrypt links, you have to limit access. In some cases, perhaps you do not have to put these devices on the internet at all, right? But these things sometimes fail, right? And there are failures because oftentimes you rely on a lot of these products to be deployed by people that don't necessarily have this in mind. We saw that there were all these attacks, this Petya virus, et cetera, and the WannaCry virus before that, put to their knee infrastructure, not necessarily the grid, not necessarily Internet of Things, but places where they should have known better, hospitals, etc. So they simply didn't install a patch that was already available. Okay, so you cannot assume that these systems will be foolproof. They will have a perimeter which is protected. Okay, and there are 2 types of attack. There are actuator attack, and there are data injection attack. And the actuator attacks are obvious. You start messing up physical stuff because you can. And the data attack is instead blinding the operators or blinding the control programs from doing the right action because they're feeding junk to these control programs. Okay, so these are different attacks. Here, this last part of the slide, for those that are interested in looking at it, contains a few interesting cases. I will go quickly through a couple of them. And also the idea that you have to make a sensor network for the sensor network, or you have to embed it in the sensor algorithm itself, which has to check for intrusion in the network, for anomalies that happen in the way the network is used, right? And this idea of intrusion detection is very common in IT, but not in cyber physical IoT type of applications, right? So in fact, a lot of the products that are put in place, they put a sensor network on top of the network, and I think that's very inefficient, right? It's very costly, it's very inefficient, it's very difficult to maintain. Okay, so I don't have a lot of time, obviously, left to talk about it, but there have been studies that have essentially demonstrated that there are a lot of common attacks that you can perform in SCADA system. One is, of course, unauthorized access. Man in the middle, you just take packets and replay them at a different time to have an actions made. You can have device installation, and these devices are rack devices. denial of service attack, malicious software patching, and all kinds of things. And there are very well-known cases in which this was obtained. In the case of the Stuxnet virus, the way the virus was injected in the system was physically through a USB stick, right? So this was a virus attack that was done to the Iran nuclear power plants. They basically made a software patch to Siemens PLC that made the turbines that were in this power plant, they were enriching uranium, they were made and spin out of the shaft, just destroy themselves. And all meanwhile, the operator was looking at the screen and everything was perfectly normal, right? So they were replaying all data to the operator. So the operator thought everything is merry and nice, okay? And then this was, you know, a really sophisticated effort. Unfortunately, then the virus was spread out and people became really concerned about this. Then there was another incident, and in this case, again, the breach was by an employee that was disgruntled, and what happens is that this was a water plant, actually, it was not a power plant, and millions of liters of untreated sewage was put in the drinking water, right? Not nice, okay? So these are serious problems that have huge economic and social impact. Another grid attack was the attack in Ukraine. Arguably, this didn't have a lot of impact in the sense that only 0.001% of the production was stopped, but it spooked a lot of people. Okay, and this actually was staged remotely. Okay, so there is a lot of reason of worry, right? And the rest of these slides, which are a few slides, just talk about what kind of criteria you can utilize to detect that there is an intrusion in your network, assuming that it's possible to breach whatever firewall or protection or authentication that you do. And really, I think the work that I've done specifically is intended for power systems and is trying to use both data about the communications and physical data to figure out if the network is operating correctly or it's under attack. But I think this is something that can be definitely generalized, because if you see strange things, you have a lot of correlated information that you can get from other sensors, on other actuators that are not under attack, that can be used to figure that out. And so that is another process that you should have online in these networks. With this, I conclude. Thank you for being so patient listening to me. And I'm happy to take questions online or offline.